The next section is about the vector model. Now you might wonder really why we will spend so much time on this, because the vector model is a picture of NMR that's extremely limited. It only applies to uncoupled spins. So you can't describe any interesting experiment with the vector model at all. So you think, well, that's a kind of strange thing. Why waste so much time on it? And the reason is several-fold, in fact. First of all, that this is a model which is geometrical, which is thought of, you can think of in rotations and things actually happening in real space. So it's actually something that's very easy to get hold of, because it has a sort of physical reality to it. And in particular, it doesn't involve any quantum mechanics, so you're not worrying about operators and all this kind of stuff. So it's a simple thing to grasp. And although it's of extremely limited applicability, we can describe some very important experiments using it. The pulse acquire experiment, which is used for recording NMR spectra every day, and very important experiments like the spin echo, which we will spend an awful lot of time talking about over the course of the next few days. And finally, the language we use to describe NMR, a lot of it comes from the vector model. So when we look at product operators, which is a quantum mechanical description which will work using for coupled spins, we're going to use language which comes from the vector model. So I make absolutely no apology for spending time on this model which only applies to uncoupled spins, because it lays the foundations for understanding the basic experiments, and it also lays the foundation for the language which is used in most other NMR experiments. So what's the idea behind the vector picture? So it starts from the following point of view, that if you think about an individual nucleus, it has what's called a nuclear spin magnetic moment. That's the property of the nucleus which gives rise to an NMR spectrum. And for a very good level of approximation, you can imagine that each nucleus generates a little magnetic field. It acts like a small bar magnet. Technically, you would say it's a magnetic moment, a magnetic dipole. So you've got this idea that you've got each nucleus, and each nucleus has this little magnetic dipole or magnetic moment. And it's this magnetic moment that interacts with the magnetic field that you apply. So you've got your spins there, each of which has a little magnetic moment. You apply your big, strong magnetic field from the magnet, and there's an interaction between them. And this interaction, of course, is what we study in NMR. And then you have to understand that, of course, in your sample, you've got an enormous number of these spins. So what you actually observe in the experiment is the average behavior of a very, very large number of spins. But each individual spin is behaving like a little bar magnet. Right? That's the key idea. Each spin like a bar magnet, like a magnetic moment. What you observe, though, and what we've got to think about, is the average of a very large number of such small spins. Now, when you put these spins in a magnetic field, they have an energy due to the interaction between the magnetic field that you apply and the little magnetic moment that the spin has. And this energy of interaction, in fact, goes as the cosine of the angle between the magnetic moment and the big applied magnetic field. And so if the magnetic moment was aligned with the field, you'd get the lowest energy. And if it was lined against the field, it would give you the highest energy. And the crucial thing that you have to grab here is that this angle, this alignment, can be at any angle. Right? Now, this is something that you may have been told the following, that the spins are up or down. This is not true. Right? I'm sorry, it just isn't true. Right? The spins can be aligned at any angle with respect to the magnetic field. If they were up, they would have the highest energy, lowest energy, and if they're down, they'd have the lowest energy. Right? But it's not true that they have to be up or down. They can be anywhere in between. Right? And you really must let go of this idea that they have to be up or down, otherwise none of the rest of this makes any sense at all. So the picture you have to have in your mind is there are all these spins in the sample, and every one has a little magnetic moment, and these magnetic moments are pointing all over the place. So on the left there are the individual magnetic moments, pointing all over the place, and here's the applied magnetic field that you've put on. And you remember that what you actually detect is the average, the sum of all of these individual magnetic moments, and we call that the bulk magnetization. So you have to imagine each of these little arrows as a vector, and you have to add up all those vectors, and that gives you the total magnetic moment, the bulk magnetization from the sample. And it's this bulk magnetization is the thing that you observe. It's the thing that's actually detected in an NMR experiment. And the vector model is all about this bulk magnetization. And remember, it's the sum of the individual magnetic moments. Now, before we proceed, we should just have a little word about the axis system we're going to use. And we're going to consistently use a right-handed axis set, which is like this, and a positive rotation is described in this way. So if you want to rotate in the positive direction about Z, you have to grasp the Z-axis with your hand and point your thumb along the plus Z direction, and then your fingers curl in the sense of a positive rotation. And unfortunately, the sense of rotation matters quite a lot in NMR experiments. So you may think it's a bit fussy, but we do need to be consistent about this. So what this means is that if you have a positive rotation about the x-axis, you grasp the x-axis and your fingers curl like this, you'll see that will take you from Z to minus Y. Right? So this is consistently the convention we're going to use. Okay, so back to the little magnetic moments. We take the sample and we put it in the magnet, and what do we get? Well, what we get is no magnetization at all, no bulk magnetization. Why is that? Well, if the spins are outside the magnetic field, then there's no energy preference for them to point in any direction. So basically they just point in random directions, and when you add up the total magnetic moment, it comes to 0. So if you take your sample, you put it in the magnet, to start with, there is no magnetization. There is no bulk magnetization of the sample. That's what you show there. So if there's no field, there's no magnetization. And then when you put the field on, there's still no magnetization. What you have to do is wait for a certain amount of time, maybe a few seconds. And what will eventually happen is that you will get a Boltzmann distribution established, by which there's a slight preference for those orientations with a lower energy over those orientations with a higher energy. So remember, the lower energy orientations are the ones where the spins are closer to plus Z, and the higher energy ones are the ones where they are closer to minus Z. So you get the bulk magnetization arises from this unequal distribution of orientations. Now, because the energy of interaction of the spins with the magnetic field is so small, this alignment is very, very tiny, and that's why I've really drawn it as if they're still randomly aligned. You shouldn't think that all the spins suddenly go like this when you put them in the magnetic field. They don't. They barely change at all in their distribution, but there's a very slight preference for them to be aligned in the plus Z direction over the minus Z direction. So this gives rise to a bulk magnetization. All right, that's a property of the whole sample. That's indicated by the blue vector at the bottom, and it's aligned along the plus Z axis. Question is, why is there no X or Y component? I've shown it as being aligned along plus Z. These spins could be aligned in any direction, so each individual spin has an X and a Y component. The reason that there's no x or y component is that there's no energetic preference over pointing in plus x than there is in minus x. There is an energetic preference in plus z over minus z, but not in x or y. So the spins are distributed randomly in x and y. So when you add up the magnetization in that direction, there's no magnetization in the xy direction. So you put the sample in the magnetic field, you wait for it to come to equilibrium, and lo and behold, this bulk magnetization appears along the z-axis. And the vector model is all about what happens to that bulk magnetization. From this point onwards, we stop thinking about the individual spins. It just focuses on this bulk magnetization. Now, unfortunately, it actually doesn't do anything at all. It just sits there along the z-axis, and that's all that happens. That's not very interesting. And in particular, there's nothing to observe. Nothing happens. Nothing changes. And if you want to get anything that you can actually observe, you need to take this bulk magnetization vector and move it away from the z-axis. Now, let's just set aside for a moment how you do that. I'll describe how you do that in a minute. But let's imagine we have done it. So we take the z magnetization, we move it away from the z-axis. What happens? Well, what happens when you do that is that this magnetization vector undergoes what's called a precessional motion about the z direction. And what that means is that the magnetization vector maintains a constant angle to the z-axis, and it goes round and round on a cone. That's called a precessional motion. And lo and behold, the precessional frequency is exactly the Larmor frequency that we defined when we were talking about energy levels. That's not a coincidence, by the way. I mean, it's the consequence. So the picture is this. The magnetization is there. You move it away from the z-axis, and then it goes round and round like this, and it goes round and round at the Larmor frequency. Now this is now detectable because you've got something that's changing over time. So what you do is you wrap a little coil around the sample. This is my attempted representation to show a coil which is wrapped around the x-axis. And the magnetization vector is going round and round like this around the z-axis. And the result is that the magnetization vector cuts the coil, and that induces a current in the coil. And then that's what you actually detect in an NMR experiment. Now, you may remember this from elementary physics class. You know, there's this classic demonstration of electromagnetic induction. You have a coil, and then the teacher pushes a magnet into the coil, and you see a current in the coil. And that's exactly what's happening here, except the magnet is the magnetization from the spins. So we can actually detect this Larmor precession directly, because it will give rise to an oscillating current in the coil, which you then detect, and it shows you on the screen in the usual way. And this is the first of many little pictures which just show you how you can describe this in little more detail using just some very elementary trigonometry. And it's one of the things that's nice about the vector picture is that the maths is very easy. So what I've done there is I've imagined that I've turned the bulk magnetization vector through an angle beta away from the z-axis towards the x-axis. So you can see that the x component is m0 sine beta. And then if you imagined you allowed that to precess, what you would end up with would be, over time, the magnetization vector would rotate through an angle. So now this picture, we're looking down the z-axis. The magnetization vector starts out along x, and then over time it precesses around and goes around such that the angle it moves through is omega naught times t. Now why is it that? The Larmor frequency is omega naught. That's the frequency at which the vector is going to go round. So if you take the frequency times the time, that gives you the angle through which you've moved. So this vector will go round and round and round and the angle will be omega naught t. And you can easily work out, therefore, that you'll get along the x-axis, you will get an oscillating signal which will go as cos omega naught t, and along the y-axis, you'll get an oscillating signal that goes as sine omega naught t. And this is the free induction signal. This is the thing that you observe in a pulse NMR experiment. Now this brings us back to the point that I started with, which is that we need to turn the magnetization away from the z-axis. Remember, if it's on the z-axis, nothing happens. You've got to rotate it away from the z-axis, and then the magnetization vector will start to do this precession. So the next part is, how are you going to turn the magnetization vector away from the z-axis? And this is, of course, going to be a radio frequency pulse. Now the problem is this, is that you've applied a very strong field, several Tesla magnetic field, along the z-axis. And you can't switch that magnetic field off, or at least if you tried to, you would be immediately dismissed from the university, because you're not supposed to quench the magnetic field. All right? So that is there. You just got to live with that. In our minds, what we need to do is to apply a magnetic field along the x-axis. Because if we did that, then the magnetization would precess in the ZY plane, because the magnetization precesses perpendicular to the applied field. But we've got no way of doing that, because the field along Z we can't get rid of. So we have to be a bit cleverer about it. And the way we do this is we use the phenomena of resonance. So the B0 field is so large, there's no possibility of dominating its effect with a field. But if we apply a weak magnetic field along X, and if we make that field oscillate at the Larmor frequency, it turns out that even though that field is very, very much weaker than the field along the plus z-axis, it can rotate the magnetization away from the z-axis. And this is the phenomena of resonance. And the analogy you might like to use for this is this business about how you pump a swing. You know, how do you get a swing going? So your little niece or nephew comes and you've got to push the swing. And being good scientists, you know that you need to push the swing in the right phase. It's no good just kind of hitting it at random. You've got to make sure that you apply the force in exactly the same frequency at which the swing is already swinging, the natural frequency of the swing. And if you do that, you can get it going. And that's exactly analogous to what you do in NMR. We know that the magnetization wants to precess at the Larmor frequency. So what we do is we apply an oscillating field which is oscillating in synchrony with that precession. And if you do that, a very weak field can actually have a strong effect on the spins, even though the field you apply is much, much less than the static magnetic field B0. Now, to analyze the effect of this, you need to use the famous, or alternatively infamous, rotating frame of reference. So I'll explain to you what this is and how it makes this problem somewhat simpler. So there's rather a lot going on in this diagram. So first of all, I want you to concentrate on the second row labeled B. And this is a view down the z-axis, and my black line, my black vector, is a magnetic field. And you'll see that over time, this magnetic field is oscillating along the x-axis. So it starts out at plus x, it shrinks to 0, and then it goes to minus x, and it comes back to 0 and plus x. So that would be called a linearly oscillating field along the x-axis. If you look at the graph at the bottom, that's what I've plotted there. So the line B shows exactly the graph. Now, for reasons that will become apparent in a minute, it's convenient to think of this linear field as being the result of two counter-rotating fields. And that's what's illustrated in line A. So what you say is, if I have two magnetic fields, one of which rotates this way, I call that one B1 plus, and one of which rotates this way at the same frequency, I'll call that B1 minus. The sum of these two is the same as the linearly oscillating field. So at time 0 they both start out here, so it's a maximum, and that one goes that way, and that one goes that way, and you can see that once we get to this point they cancel one another out, so the linear field is 0, and that corresponds to the third of the diagrams there. Now if I go to plenty of yoga classes I could do the next bit, but I can't. So you have to imagine that I could do this, all right? And that would be with the magnetic field pointing along minus x. So the two counter-rotating fields go like this, and I certainly can't do the next bit. The result of that is a linearly oscillating field. That's just something you do in your head. The truth is the field is going like this, but we can think of it as one field going one way and one field going the other way. Now, one of these fields is going to be going round in the same direction as the Larmor precession, and one of which is going to be going the opposite way to the Larmor precession. And you can take it from me that the one that's going the opposite way to the Larmor precession is going to have no effect whatsoever. So we throw that one away, so we're only going to consider the one rotating component that's going round at the same rate as the Larmor precession. So that's the first part of this, the decomposition of a linear field into a rotating field. Now we need to try and simplify the description to get rid of this time dependence. And the way you do this is you go to a rotating frame of reference. So first of all, look at the first line, marked laboratory frame. I've chosen B1 minus to be the one going around in the same direction as the Larmor frequency. And it's actually going around at a frequency minus omega Tx. So Tx is the abbreviation for transmitter, because it's the radio frequency transmitter that's going to generate this field. And it's going around in a negative sense. If you think about how I described to you what a positive and negative frequency were, that's a negative rotation. So there's B1 minus on the top line going around at minus omega Tx. And the trick about the rotating frame is if you make the axes, instead of having them fixed, if you make the axes go round at minus omega Tx, then it looks as if the magnetic field is not moving at all. So the point of going to the rotating axis system is it makes it seem as if something that was going like this is actually static. And that actually makes life much simpler when it comes to working out what happens next. So the rotating frame is just a device to get rid of the time dependence of this rotating component. And you need to remember that you all live in a rotating frame, right? So the Earth is rotating all the time, but we're completely oblivious to that, and we can describe what's going on in our rotating frame, ignoring this complicated time dependence. So if I want to walk across the room, I just walk in a straight line. I don't have to do something more complicated. So that's the rotating frame. Now, you need to put all of that to one side for a moment, and now start thinking about the Larmor precession again. So let's think about the Larmor precession. In the normal frame, in the lab frame, the Larmor precession goes at the Larmor frequency omega naught. So this thing is going round and round and round like this. But if we go to the rotating frame is going around as well. So if you look at the Larmor precession in the rotating frame, it actually appears to be going slower, because the precessional frequency will be the difference between the rotating frame frequency and the actual Larmor frequency. So for example, to take a concrete number, if the Larmor frequency was 100 Hertz, that's very slow, but anyway, if it was 100 Hertz and the rotating frame was going at 99 Hertz, when you were in the rotating frame, it would make it look as if the Larmor frequency was just 1 Hertz. So in the rotating frame, the Larmor frequency changes. Now, you have to bear in mind, I'm not saying the Larmor frequency actually changes, it just changes because you're looking at it in a different point of view. This quantity, the difference between the Larmor frequency and the rotating frame frequency, is called the offset, capital omega. We'll use this term a lot, the offset. Now, this is a little bit complicated, this bit. Now, you have to remember that there's always a relationship between the precessional frequency and the magnetic field. So, and it's omega equals minus gamma b. We've already used this in the form that omega naught is minus gamma b naught. But it works for all magnetic fields. So if you have a particular nucleus experiencing a particular magnetic field, you can always work out what the Larmor frequency, the precessional frequency is, using omega equals minus gamma b. So if you turn this on its head and say, well, in the rotating frame, the magnetization appears to be going at capital omega, what that implies is that the magnetic field must be minus omega over gamma. Right? That's just rearranging that formula. And this is called the reduced magnetic field in the rotating frame. So delta B is the reduced field in the rotating frame. So what we're saying is, in the rotating frame, the Larmor precession slows down, and you could interpret that by saying that that means that the magnetic field has got weaker. Of course, the magnetic field hasn't got weaker. It's still the same. It's just in the point of view of the rotating frame. So now we need to go back and think about our two fields. Remember, we had the oscillating field, which we decomposed into a rotating field, and we then went into a rotating frame. And that is one field, and that's along the x-axis. And we call that the B1 field. It's the field due to the applied radio frequency power. Then we've got this other field in the rotating frame, delta B, and that's the reduced field due to looking at the Larmor precession in the rotating frame. And what the spins experience is the vector sum of these two fields. So you've got one along Z, which is delta B, one along X, which is B1, and the spins experience the vector sum of these, which is called the effective field. Now, we have to choose the rotating frame frequency to be equal to the transmitter frequency, because it's only when you do that that you end up with the rotating field becoming static. And remember, because we chose this component B1 minus, it actually goes round at minus omega Tx. The minus comes about because of the Larmor precession being at minus gamma B naught. And so the offset, rather strangely, is the difference between the Larmor frequency and the rotating frame frequency. But the rotating frame frequency is minus omega Tx. So unfortunately, the offset appears to be the sum of the Larmor frequency and the transmitter frequency. Now, if that isn't confusing, nothing is. Right? It's one of these minus signs that no matter what you do, they just come back to plague you like some insect. Right? But remember, omega naught is negative, so that offset is usually a small number. So this is the picture of what you've actually now got in the rotating frame. You've got B1, that's the applied field, that's the small field that you applied along the x-axis. You've got delta B, which is this reduced field, that's the field which was originally the big field B naught, but has got smaller because you're in the rotating frame. And then the spins experience B effective, which is the vector sum of these two. So you recognize the geometry there, that B effective is just the vector sum of delta B and B1. So for example, you can work out what B effective is just from Pythagoras, the square root of B1 squared plus delta B squared. So in this rotating frame, the spins experience B effective. That's the key point. Now this angle between B effective and the z-axis is called the tilt angle. Don't confuse that with a flip angle, that's something else. This is called the tilt angle. And you can see just from simple geometry, you can work out what theta is from B1 and delta B. Now, it's normal to think of this diagram in a different way. Instead of thinking of it in terms of magnetic fields, to think of it in terms of frequencies. Because you can always interchange between a frequency and a magnetic field using this omega equals minus gamma B relationship. So every magnetic field you can write as a corresponding frequency. So the offset, big omega, is minus gamma delta B. Little omega 1 is gamma B1, and omega effective is gamma B effective. So every magnetic field has a corresponding frequency, and they're just proportional to minus gamma. So you end up here with some very strange language the first time you hear it. So NMR spectroscopists will say the RF field, which is the B1 field, and they'll give you a frequency, omega. So you think, hang on, aren't magnetic fields measured in Tesla? You say, no, it's a frequency. All right? And they'll talk about the reduced field or the offset, and that's a frequency. And they'll talk about the effective field, and that's a frequency as well. So these are all magnetic fields, but they're almost always expressed in terms of frequencies, just using this omega equals minus gamma B notation. Don't worry, you'll get used to it. So that diagram is usually drawn like this, not in terms of magnetic fields, but in terms of frequencies now. So on the vertical axis, instead of delta B, I've got capital omega. On the horizontal axis, instead of B1, I've got little omega 1. And instead of B effective, I've got omega effective. And again, you can work out the tilt angle theta in combination using just simple geometry there. So where does this get us? You may think we're not getting anywhere, but actually we've got a long way now. When we've got the radio frequency field applied, if we go into the rotating frame, the spins will experience this field omega effective, and they will rotate about this effective field. And therefore we can imagine how the Z magnetization is going to get rotated away from its original position. Now the easiest one to think of first of all is what's called an on-resonance pulse. So if we imagine that we put the transmitter, the radio frequency transmitter, right on top of the Larmor frequency. So in other words, that makes the offset, which is the difference between these two quantities, 0. So this offset field omega just disappears completely to 0. So that means that omega effective must lie along where omega 1 is. In other words, it's just along the x-axis. So if you are on resonance, as it's called, having the pulse exactly on top of the line, then the only thing that the spin sees in the rotating frame is a magnetic field along x. The Z field has miraculously disappeared completely. And under those circumstances, the behavior is actually very simple. All that happens is the magnetization rotates in the YZ plane. Why is that? You've got the magnetic field here along X. The magnetization starts along Z. It's perpendicular to it, so the precessional motion is just in the YZ plane. And that's exactly what we wanted, because remember what we were trying to do all along was rotate the Z magnetization away from the Z-axis towards the XY plane, because then we generate this processing signal that we can detect. So this is a picture of what would happen under those circumstances. So the grey arrow pointing along X is the B1 field. That's the field due to the RF pulse. And we're on resonance, so that's the only field that's present. The magnetization vector starts along plus Z, and then when we apply the field, it rotates in the ZY plane. And the blue line is the path that the tip of that vector would take. And I've chosen to draw there a 90-degree pulse, and that means that I choose the duration so that the magnetization goes from Z into the transverse plane. So the angle that it's gone through, which is called the flip angle, is 90 degrees. And then once you get to the XY plane, you switch off the radio frequency power, and then you've got what you want. The magnetization is in the XY plane, and it will process around, and you can detect the free induction signal. Of course, you don't have to do that. If you leave the pulse on for longer, it will start on plus Z, it will go down to minus Y, and if you keep on, it will end up on minus Z. And now the total rotation is 180 degrees, and that's called a flip angle of 180 degrees. So you can do either of these in this way. And again, the geometry of this is very simple. Here's the magnetization vector starting along Z, and then it's being rotated through an angle beta. That's the flip angle. And you can see that the Y component is proportional to sine beta, and the Z component that is left over is proportional to cosine beta. That's just simple geometry. And obviously, if you want to create the largest possible transverse magnetization, you need to make the flip angle 90 degrees. That will take the magnetization all the way from Z down onto minus Y. Now that's all very well, but you can't be on resonance with all of the lines in the spectrum. You've got several lines in your spectrum normally. You could put the transmitter on top of one of them, but you couldn't do that for all of them. You've got to choose one place to put it. But if you make the radio frequency field, the B1 field, strong enough, you can effectively achieve this to good approximation for all the lines in the spectrum. So let's do a little calculation to see how this might work. Suppose you had a proton spectrum that's 10 ppm wide, and suppose you decide you're going to put the transmitter in the middle of the spectrum at about 5 ppm. Then the largest offset you could have would be 5 ppm, right? Because a peak at 0 would be 5 ppm away, and a peak at 10, that would be 5 ppm away. And let's imagine it's a 500 megahertz spectrometer, so 5 ppm translates to 2,500 hertz. So the maximum offset, omega, is 1.57 by 10 to the 4 radians per second. I would get that just by dividing the 2,500, multiplying it by 2 pi. Now, a typical value that you might find on the spectrometer would be 12 microseconds for a 90-degree pulse. Now, that means an on-resonance 90-degree pulse. In other words, it would take you 12 microseconds to go from Z into the transverse plane. Now, the angle is omega 1 times the duration of the pulse Tp. So we can work out from that 12 microseconds what omega 1 has to be. It's beta, the angle, which is going to be pi over 2, divided by the length of the pulse. And if you work that out, you'll work out that omega 1 is about 1.3 by 10 to the 5th radians per second. So that's the omega 1. And you can work out also the tilt angle. That's the angle between the effective field and the z-axis, and that turns out to be about 83 degrees. So this is actually the picture that you've got. The offset is rather small. Omega is quite small. Omega 1 is rather large compared to the offset. So the effective field is almost along X. Now you remember, for an on-resonance pulse, the effective field is exactly along X. For this, it's almost there. So what you would say is that this pulse would be described as a hard pulse, and that means it's sufficiently strong, that omega 1 is sufficiently big, that over a range of offsets, it produces a field that's almost along the x-axis. Now, whether 83 degrees is close enough to 90 to matter depends on the experiment, but this is typically what you would do. So when you've got a spectrum and you put the transmitter in the middle, the lines near the middle, those spins, experience an effective field which is very close to x. And the ones at the edge of the spectrum, the effective field is tilted up a bit, and you hope that it isn't tilted up too far. That's why you use a strong pulse. That's called a hard pulse. Now, one last thing before we move to look at some experiments, and that is what you actually detect. I said that if you turn the Z magnetization away from the Z-axis, this magnetization would precess around, and that would cut the coil, and that would give you an oscillating signal at the Larmor frequency. Now, in practice, because of the way the spectrometer works, it turns that frequency, which could be quite a high frequency of several hundred megahertz, into a much lower frequency. And actually, it usually does it by subtracting the transmitter frequency. In other words, the frequency that you detect is not the Larmor precession, but this offset frequency, big omega. All right? So when we talk about the detected signal, and the signal you see on the screen, that frequency is not actually hundreds of megahertz. It's this offset frequency omega, which is typically much, much smaller than that. And so from now on, we'll do that. So for example, if we've done a pulse of flip angle beta, then the x component would be something like sine beta, and then we would allow it to precess, and the precession would be cos omega t. It's omega, the offset frequency, not the Larmor frequency. But I emphasize that that's just a consequence of the way the spectrometer works. The spins, of course, are themselves going round at the Larmor frequency. So what I now want to do is to use the vector model to describe three experiments, the pulse acquire experiment, pulse calibration, and then most importantly, the spin echo. So here's the standard pulse acquire experiment that is used all the time to actually record spectra, and it comes in three parts. First of all, you have to let the spins come to equilibrium, and that might take a few seconds, and that's to allow the magnetization to build up along the z-axis. And then we have a 90-degree pulse, and I'm going to assume that this is a hard pulse, so that will rotate the magnetization from Z nicely onto minus Y. And then you switch the RF field off, because you've got it where you want, and then this magnetization vector will precess in the transverse plane, and that will be the thing that you detect. And that will give you an oscillating signal, as I've shown there. And the geometry of this is very straightforward. These pictures are looking down the z-axis. So the 90-degree pulse puts the magnetization vector along minus y. And you remember that the vector is going to go around not at the Larmor frequency, it's going to go around at the offset frequency, big omega. So if we wait a time t, the vector will have moved through an angle big omega times t, which is shown there. And just geometry tells you that the y component goes as minus cos omega t, and the x component goes as goes as sine omega t. And they are plotted there. And in fact, on a modern spectrometer, you would detect both of these components of magnetization. So that's how the pulse acquire experiment works. And if you want it with arms, it's Z down to Y, minus Y, and then the magnetization vector goes round. That's what you detect. Now, of course, in practice, relaxation would eventually make that magnetization decay away, but that's not included in this vector picture. The second experiment is to do with calibrating the pulses. Now, Obviously in these experiments, when I say, well, I want a 90-degree rotation, how do I know what length pulse to apply to get a 90-degree pulse or a 180-degree pulse? And in general, you have to calibrate that and make sure you find out exactly what it is. So in fact, what you do for pulse calibration is you do a pulse and then you acquire the signal and you measure the spectrum. And then you do the same thing again, making the pulse a little bit longer, making the pulse a little bit longer, and so on. And typically what you might see here is that as you make the pulse longer, to start with, the peak gets more intense, and that's as you're approaching a flip angle of 90 degrees. And then after that, the spectrum gets weaker as you approach a flip angle of 180 degrees. And when the flip angle is 180 degrees, you see no signal at all. That's because if you start on plus Z and you go down to minus Z, there's no transverse component to detect. And if you go beyond 180 degrees, you'll see a negative signal because you're generating plus Y rather than minus Y. And in fact, the normal procedure is to increase the pulse length and look for the zero crossing at 180 degrees. And the reason for doing that is that this zero crossing is usually more sharply defined than the 90 degree, because the 90 degree is a kind of flat plateau. The 180 degrees, it's crossing through zero. So the experiment you would do, you would increase the pulse flip angle until you saw no signal, and that would be a 180 degree pulse. Now, how can you work out what the omega-1 field is from that? Well, remember that the flip angle is omega-1 times the duration of the pulse, Tp. So if you want to work out what omega-1 is, it's just beta, the flip angle, divided by Tp, the duration of the pulse. So let's suppose we've determined, in the way I've just described, that the 180 degree pulse is of a length T180, then that means omega-1 must be pi, which is the flip angle, divided by T180. And of course we have to put the angle in radians here. And if you want the field in hertz rather than radians per second, you need to divide by 2 pi. So the field in hertz, omega-1 over 2 pi, is just 1 over twice the length of a 180. And of course you'll recognize that twice the length of the 180 is actually the time for a 360. And so that's just 1 over the period, which is the frequency. So to take a concrete example, suppose you determined the 180 degree pulse was 15.5 microseconds. You could work out from that, using that formula, that omega-1 was about 2 by 10 to the 5th radians per second, which is 32.3 kilohertz. So if you ask someone what the B1 field is, and they just calibrate it like this, they would tell you it's 32.3 kilohertz. And again, it's that rather funny thing. I asked you what the field was, and you told me a frequency, but fields and frequencies are interchangeable. And in fact, the frequencies are always much more useful than the fields. So that's how you could determine the value of omega-1. Now, the third experiment is the one that's much more important than the other two, and that is the spin echo. As I said before, we're going to spend a lot of time thinking about spin echoes because they are an absolutely crucial building element in more complicated sequences. So what is a spin echo? Well, this is the pulse sequence. You do a 90 degree pulse, you leave a delay, and then you do a 180 degree pulse, and then you leave the same delay, and then, and only then, do you observe the signal. And in these diagrams, a solid block is a 90 degree pulse, and an open block is a 180 degree pulse. And notice I'm indicating you acquire the signal after the second delay tau. And this spin echo has a very, very important property, and that is at the end of this sequence, where the acquisition starts, no matter what the offset omega is, and no matter what the time tau is, the magnetization vector is always in the same position. So this sequence puts the magnetization vector in the same position for all values of tau and for all values of the offset. In fact, we describe this by saying that the offset has been refocused, and that's because of the way the spin echo works. So in other words, although the magnetization precesses during the delay tau and also during the second delay tau, at the end of the sequence it is as if it hasn't precessed at all. Now that may strike you as being perverse. You know, why would anyone be interested in that? But this turns out to be a crucial idea, this idea that you can leave time, but at the end of it make it look as if no time has been left. That's why it's called an echo. So we're going to look at how this works in using the vector model. How does it achieve this remarkable property of returning the magnetization to the same position regardless of where you started? And the first thing we need to do is to worry about this 180-degree pulse, because I've described to you what a 180-degree pulse does if you start on Z. So if you start on Z, a 180-degree pulse rotates you to minus Z. But in this sequence, the magnetization when the 180-degree pulse is applied is in the XY plane, because we've done 90, let's put it down on minus Y, and then it's precessed around in the XY plane somewhere. So the first thing we need to do is to say, what would happen if we applied a 180-degree pulse in a situation where we've got X and Y magnetization? And that's what this picture here is trying to illustrate. So concentrate on the dark blue vector first. So that's a typical magnetization vector. It's at some kind of arbitrary position in the XY plane. And the 180-degree pulse is a rotation about the X-axis, which is coming towards us. And the dark blue line is what happens to the tip of that vector during the 180-degree pulse. And you'll see what it does is it takes it on a path and it brings it back to the XY plane. Now if you look at the pale blue vector, the same thing happens. And the even paler blue vector, the same thing happens again. And in fact, what we're going to show a little bit more carefully in a minute is that what this 180-degree pulse does is it puts the vector in a mirror image position with respect to the XZ plane. So if you think about the starting position and the ending position, they are mirror images with respect to the XZ plane. So the effect of this 180-degree pulse is to move the magnetization vector to a mirror image position with respect to the XZ plane. Now let's see that in a slightly more formal way. So here we are again with the vector. This time we're just looking down the Z-axis. And I'm saying that after a time, it starts out on minus Y. And I've allowed it to evolve for a little bit to some arbitrary position, which I can describe by an angle phi. So it's just moved through an angle phi. Now it's convenient to take this vector and separate it into its X and Y components, to resolve it into its two components. So that's just a bit of geometry. So there's a component along minus Y, and there's a component along X. And if you add those two together, you'll get the vector that I showed you there. So it's just resolving into its X and Y components. Now imagine applying the 180-degree pulse. What does the 180-degree pulse do to the component along X? Answer, nothing. Because if the magnetization is along X, and you rotate about X, that has no effect at all. So an X rotation of the X component of magnetization does nothing, because you're rotating about the axis along which the magnetization is aligned. So that 180-degree pulse, that does nothing to the X component. What about the Y component? Well, the magnetic field is along X, the magnetization is along Y, they're 90 degrees to one another. So if you do a 180 degree rotation, it just flops it over from minus y to plus y. That's just like the magnetization going from Z to minus Z. Right, so the 180 rotation about X takes minus y to plus y. So now I can recombine those components, and of course the vector is now pointing downwards to the right, as is shown on the final diagram. And you'll recognize that if you compare the starting position and the final position, they are in a mirror image with respect to the XZ plane. And if you want to describe it in terms of an angle, you need to be quite careful. I'm going to define the angle as being measured anti-clockwise from the minus y-axis. So if you look at the first picture, phi is measured anti-clockwise from the minus y-axis. So the angle that my vector ends up at is actually pi minus phi. You have to be consistent about measuring it in the same direction. So it's still phi away from the horizontal, but the angle measured all the way around is pi minus phi. Okay, so that's the effect of the 180 degree pulse. It takes the vectors to a mirror image position with respect to the XZ plane, and we can describe it as changing this angle from phi to pi minus phi. So having done all of that, we are in a position to describe the spin echo now. So look at the sequence of diagrams along the top first of all. Ignore the bit at the bottom. At time, this is shown immediately after the 90 degree pulse. The magnetization is along minus y. And then it starts to precess, and then a bit more, and just before the 180 degree pulse, the angle through which it's precessed is omega tau. And it's omega tau because the offset is omega and the time is tau, so the angle is the product of those two. Then you do the 180 degree pulse, and remember the 180 degree pulse takes the vector to a mirror image position with respect to the XZ plane. And that's exactly what you see there. The XZ plane is vertical in the diagram, and the vector's flopped over onto the other side. And of course the angle measured in the same sense is now pi minus omega tau. And then you just let it precess a bit more, and of course over the next tau period it's going to precess through another angle of omega tau. So by the time you get to the very end of the sequence, it's going to be along the y-axis. Right? Because during that second tau delay, it precessed through exactly the same angle as it did during the first tau delay. And that will be true no matter what the value of omega and no matter what the value of tau is, because you'll always get this behavior here. Now have a look at the graph underneath, which is just another way of describing this. Let's concentrate on the blue line, and the blue line shows how the phase changes over time. And remember, the phase is this angle that I've shown there. So to start, it starts out at 0, indicated by the red arrow here. And as the time increases, the phase increases, shown by the green arrow here. And then just as you get just before the 180 degree pulse here, the phase is its maximum value. And then the 180 degree pulse changes the phase from phi to pi minus phi. And that's exactly what we've got there. The phase goes from omega tau to pi minus omega tau, and that's what the 180 degree pulse does. And then the evolution continues so that right at the end the phase is pi. Right, so the diagram underneath is just a different way of describing what's happening at the top, where we just plot the angle rather than draw the diagrams. It isn't a different explanation. And if you think about the grey line on the bottom diagram, that's actually for a smaller value of the offset omega. So it increases more slowly. So when you get to the 180 degree pulse, the angle is smaller, but the 180 degree pulse takes it to this mirror image position, and it still ends up exactly at the same end point, even though the frequency is different. And that's this special property that a spin echo has. It refocuses the offset. Now, just to finish up with a couple of other things. First of all the pulses I've described so far have been rotations about the x-axis. So I've said when you apply a pulse, it rotates about x, and for example, that takes the magnetization from z towards minus y. Now, the spectrometer usually gives you the option of applying the radio frequency field about any axis you like. So, for example, you could apply the field about a y-axis, and if you did that, again, if you think about grasping the y-axis with your fingers, you'll realize that that will rotate z towards x. So what I'd illustrate here is a 90-degree y pulse, which takes you from z to x. And if you want to, you can do something like a 90-degree pulse about minus x. So there the magnetic field is pointing along minus x, and if you grasp the field with your fingers, you'll see that that will rotate z to plus y. So you don't have to apply the pulses about x, you can apply them about any axis you like, but you need to use this sphere to work out what's going to happen. Now I want to come back to thinking about this business to do with the effective field. So it's this diagram here we had, where the spins experience this effective field, which is the vector sum of the offset omega and the radio frequency field little omega 1. Remember we said that if you were on resonance, or if you had a strong pulse or a hard pulse, then basically you can ignore big omega and the effective field lies along the x-axis. And then you end up with quite a simple picture. What I want to now consider is what happens if omega is comparable with omega 1 so that the effective field starts to tilt up. What consequence does that have? And that's shown in this diagram here. So there's quite a lot going on here. So first of all, concentrate on capital A and little a, which are circled in red and green. So first of all, these show an on-resonance pulse, and therefore the effective field is along the x-axis. And capital A shows the direction of the effective field by this dashed line. And then little a shows the trajectory that the magnetization vector would take if it started along z. So as we've described, if you're on resonance, a 90-degree pulse takes you from z to minus y, which is exactly what's shown there. Now imagine you go off resonance so that this effective field starts to tilt up a bit. Shown in B is a tilted field. See, it's tilted up from the x-axis. And now the magnetization, instead of going cleanly from z to minus y, it makes a precessional motion about the effective field, which is a more complex path, and it makes this curving motion. It comes towards the xy plane, but it actually has an x component as well as a y component. And if you go further off resonance to C, the effective field tilts up even further, and you'll see the magnetization curls even more. And if you go even further off resonance, you end up, as is shown here, D, with the effective field right up here, and you'll see here that the magnetization vector never gets to the xy plane. In fact, it gets closest to the xy plane along the x-axis. So what does this tell us? It tells us two things. As you go off resonance, instead of the pulse just generating y magnetization, it generates a mixture of x and y. That's what those paths B, C, and D show you. And they also show you that as you go off resonance, you generate less and less total transverse magnetization. So A is the only one that actually made it all the way to the transverse plane. None of the others did. Now you can calculate this out exactly, and that's what's shown here. There's a plot of the y magnetization as a function of the offset big omega. And of course it starts at a negative value, because when you're on resonance the magnetization is minus y. And then as you go off resonance you get this rather complicated behavior. It goes through nulls and it oscillates. If you look at the X magnetization, on resonance it's 0, and as you go off resonance it starts to increase, and then it does this kind of oscillating thing. So what this tells you is that when you go away from this on resonance condition, you generate a mixture of X and Y magnetization, and exactly what you get depends on exactly what the offset is. Can get quite complicated. One way of simplifying the view here is to take what's called the absolute value of the magnetization. That's the square root of mx squared plus my squared. So just taking the magnitude. So that's squaring those and taking the square root. And what you get is, of course, a maximum on resonance, and then it drops away and has this kind of bouncing pattern. Now, if you want to excite the spins efficiently, you've got to make sure you're working within that very, very small center region where the magnetization is almost 1. It's no good trying to work on these edges where you may or may not get any excitation. So when we're talking about a hard pulse or a non-selective pulse, it's a pulse which is working on that flat region, which is very close in to 0 offset. On the other hand, you could see this as an advantage, because sometimes you've got a spectrum and you only want to excite part of the spectrum. And you can do this by deliberately making the radio frequency field weak and hoping that the lines that you don't want to excite fall well away from the center region and so are not excited strongly. And this is called a selective pulse. So if you, for example, had a spectrum with several lines in it and you excited it with a hard pulse, you'd expect to excite all of the lines evenly. What you can do is put the transmitter on this line here, reduce the radio frequency field strength so that these other lines have large offsets, and the result of that would be what we call selective excitation, where you excite the pulse, the line on resonance efficiently, and the other lines are either not excited at all or are only excited very weakly. And that turns out to be a very useful thing to be able to do in all sorts of experiments where you only want to excite certain resonances. So we can just finish up by contrasting hard and soft pulses. So you can work out relatively easily that if you want to excite 90% or more of the magnetization, you need to have offsets only between about 1.6 times the field strength. So that's actually a rather narrow range. Outside that, the magnetization drops off very quickly. And what that means is that if you've got a very wide range of frequencies that you want to excite, for example, a nucleus with a very large shift range on a high field spectrometer, you'll need a very intense omega-1 field, and that means short pulses. On the other hand, if you want to turn it the other way round, if you want to excite part of the spectrum selectively, then all you need to do is to reduce the radio frequency field so that you only excite the part of the spectrum that's near to resonance, and the rest of it won't be excited. And of course, if you make the radio frequency field weak, you need to make it weaker than the frequency separation of the nearest lines, and the consequence of that will be that the pulse will be rather long, because in order to get a certain flip angle, if you made omega-1 small, you'll have to make the pulse long. So when people talk about non-selective pulses, they're pulses with large radio frequency fields and durations measured in a few microseconds. Selective pulses will have much weaker fields and will have durations measured often in milliseconds or tens of milliseconds. But one of the problems with selective pulses is that they don't generate uniform X or Y magnetization across their bandwidth. If you looked at those plots, you'll see that the X and Y magnetization changes quite rapidly across the excitation window, and that can be a problem in some experiments. And there are a whole range of more sophisticated selective excitation techniques designed to get round that. And that really brings us to the end of our discussion of the vector model.